All right. Sorry, we're looking at transformations of trigonometric functions today. The main focus is going to be the tangent function, but I'd like to start off with a cosine function. Have a go at sketching the function y equals cos x for the interval 0 to 360. Okay, a few of you need some practice on that one. So make sure your diagram is big enough. Make sure your scale is large enough. My scale is looking a little bit small here. So I'm just going to stretch it a little bit so I can draw this more easily. This should help me a little bit. I haven't got the best axes. So to draw a trigonometric function like this one, you want to start with the 5 key reference points. So this function is going to start off at 0, 1. It's going to cut the x-axis at 90 or pi over 2, depending if you're drawing in radians. I saw some of you drawing in radians. It's going to hit -1 at 180 or pi. It's going to cut the x-axis again at 270 or 3 pi over 2. And it's going to come back up to 1 at 360. These are the 5 key reference points to draw a cosine function. You should start by plotting these and then draw your function. It shouldn't take you that long to draw this function. You don't have to have any axes of scale. So if you're drawing it by hand, you should use a ruler. You should draw your axes with a ruler. Takes you a second. Like this. You should plot your key points. You should label them. I'll do this as 3 pi over 2, pi over 2, pi, 2 pi, 1, -1. This is how we sketch a curve like this. It doesn't take 10 minutes to do this. It should not take 10 minutes. Okay, have a go at sketching this one. We have a few transformations, so think about your 5 key points, plot them, draw the principal axis, sketch the curve. Let me show 2 techniques for this one. One when we're drawing it on graph paper, and one when we're just sketching it on blank paper. Slightly different approach. The first thing you need to do is you sort of examine and look at what the transformations are. You should be able to very easily at this point in the course now. We have a vertical shift of 1. We have a vertical stretch of 3. We're struggling a little bit with a horizontal stretch compress. This one is a horizontal stretch of 2. So the period is going to become 4 pi. If you're not certain of it, you've always got the formula where the period is equal to 2 pi over b. So we've got 2 pi over a half, which is 4 pi. The period is 4 pi. This might needs a little bit of calculation. So then sketching it, we start off with drawing our principal axis. We need to draw a dotted line with our ruler along here. Then we can plot our points. So the first point, which is normally at 1, has been stretched up by 3. So we go 1, 2, 3 up. It's going to go there. It's going to cross the principal axis. Normally it would cross the principal axis at pi over 2, but now it's going to cross the principal axis at pi because the period has been doubled. We're then going to reach our minimum. We normally reach our minimum at pi. We're going to reach it at 2 pi. So the minimum is going to be 3 down from this. 1, 2, 3. So it's going to be there. It's going to be here. We're going to rejoin the principal axis at 3 pi. And we're going to come up to our maximum of 4 pi. We've got 5 pi drawn there on the graph, so we should be back down to the principal axis by that point. We could be back down to the principal axis at this point. We could be down to a minimum at minus 2 pi, so that would be there. So it's going to look like this. If you wish to draw this without graph paper, it's even quicker and easier. So you just use your ruler and draw some axes. Draw your principal axis. Draw your curve. Oops. And then just label the points. 0, 4, pi, 1, 2 pi, minus 2, 3 pi, 1, and 4 pi, 4. And at that point, I've shown all the key information that shows I have an understanding of the transformations of this sketch. This is the best sketch, and it's super quick to do. You start just by drawing the curve, and then don't worry. Even if you're working on squared paper, if you wanted to do it like this, then you can just draw it and then just label the points and explain it. If you're given graph coordinates to draw on, like we were here, the examiner's going to be looking that you get it in the right places. So even though I've missed it slightly here at pi, 1, I've shown the point I'm meaning to go at, and you'll probably get marked that one correctly. As long as it looks roughly okay and the points are marked, it should be okay. All right, tan x. How does this function look? I'm just going to show you how to draw the tan x function. So can we think about tan values from the exact value table? So in the exact value table, we have pi over 6, pi over 4, pi over 3, pi over 2, and 0. Our tan values for this are 0, 1 over root 3, 1, root 3, and then not defined. It's not defined. Notice it's getting bigger and bigger. So the standard function is going to have a vertical asymptote at pi over 2. It's going to have another one at minus pi over 2. It's going to go through pi over 4 or 45, 1. So it's going to go through this point and this point. This is our key points. It's going to go through 0, 0. So this is 0, 0. This is pi over 4, 1. This is minus pi over 4, 1. And our asymptotes are at pi over 2. And the curve looks like this. And then it repeats. So if I want to continue the curve, this is a period of pi. So this is pi over 2. This is 3 pi over 2. So our next asymptote would be there. It's going to go through this point. It's going to go through this point, it's going to go through this point, and it's just going to keep repeating like this. This is how the tan function looks. You can copy that down. So the key information there is where the asymptotes lie, the vertical asymptotes. These are at 90 degrees. These are at 90 degrees and they're separated by a period of 108. These are pi over 2 and they're separated by a period of pi. That is the crucial info. The asymptotes. This is all about the asymptotes, this graph. You get the asymptotes, you basically got the graph. The reference points are useful for stretching, showing stretches. Vertical shifts. Absolute key information is this idea that the asymptotes are pi over 2 plus periods of n pi. 90 degrees plus periods of 180. I still generally remember 90 degrees plus periods of 180 and then translate it in my head as radians. Radians is sort of harder to remember. The period's not hard to remember, n pi, but the pi over 2 type thing, fractions just don't stick in my head as well as 90. I feel like in touch. Pi over 2 is like, what? It feels a lot more abstract, so I don't memorize things that well, that way. Okay, let's have a go at sketching this one. Sorry, let me just we haven't really done it, let me just put it on here. So the asymptotes have a period of n pi. The periodic of the tan function, we haven't realized, this is the period. The period describes how long it takes for the function to repeat itself. And the period for a tan function is pi. The period is pi. So if you calculate what the new period is, that's the new distance between the asymptotes. For a sine function, the period is when it completes an entire cycle. For a cosine function, when it completes an entire cycle. That's your period. For the tan function, the period is between the asymptotes. So that's also when it completes a full cycle and repeats itself. When we solve sine function questions, we have a period of n2 pi, cosine n2 pi, with tangent, it's a period of n pi, pi. So find your period, that's the distance between the asymptotes. Draw them first. Draw the asymptotes first.
Is it still 2 pi over b?
No, it's pi over b. Good question. Because it's the standard period divided by b. Pi over 2 plus n pi.
Whoa. It's pi over b, right? And b is 3 over 2. B is 3 over 2.
Yes.
So pi divided by 3 over 2 is just 2 over 2.
So, oh, it's 2 pi over 3.
Yeah, 2 pi over 3. 2 pi over 3.
Yes.
So you have that. You often forget to include the pi when you start thinking about these sort of actual fractions. Yeah, it's 2 over 3, no, pi over 3.
So 2 pi over 3. Yeah, that's what makes that
Just write it as 2 pi over 10.
it's between pi over 2 and pi. So I'm just putting it in the
You don't need it.
just draw it.
Two pi over 3. Okay.
No. Where's your roll? Picking up on this one, right? This one? Okay, that's one. It's gonna be pi over 3.
Why?
Because pi over 3.
Why is it? Yeah.
Yeah, but like, why is it a number? Shouldn't it be like pi?
I'm smart at this. I'm thinking better than Two pi over 3. Okay, now I have to do this 10 thing.
So no, sorry, the 3 pi over 2, sorry, 3 pi over 2. So 3 over 2. Okay, it's not.
That's
Who is the first?
This is the distance between the two asymptotes. What's pi over 2? That's okay. She get it.
So the second
Drop pi over 3.
That makes sense. So.
2 pi over 3.
Yeah.
First asymptote.
Yeah, the second is 1 by 5. It's a small thing.
What is the rate?
You did your best. Same as we did our best. They either pay for the week or do nothing in the game or do lucky shot. They usually create in game. The option I came out in the game is penalty.
This is what?
1 over 2 times 1 over 2 times this.
2 pi over 3 was pi over 3.
Yeah.
Oh no.
And this one, the one that I'm between.
Oh, yeah.
The point's still, my point's still scattered. So that's because then our this is
What about 1 over 2?
Right, to replace this. Are we gonna get it right?
Why would get smaller?
Why would get that? It's annoying. Have you seen my
Yeah. Even if you put it points, you have to like count.
So, was it, what were we like, yes, I was curious. Oh, it doesn't. What this, what's this? What is this? Negative. This is supposed to be power. So, how does that come back? Oh, wait. Now, here, this one, they cancel each other. See?
Yeah, but see guys, there's only 2 points. Two?
No, look at this. Stop. Look at this. This is what, this and this cancel each other. Yes, two apart. The only way that it's not.
It just came three.
Zero.
Ignore that for a second.
Okay, yeah.
So it's, how do we get to the within
What's it very fast?
You'll be allowed to use a calculator in the major.
So let's say, so that means maximum. So this is. We don't want to. Right? So that means by is that cheaper?
Are we ready? Alright. Okay. So we need to figure out where the first asymptote is going to be. You can figure out, where does it normally lie? So you need pi over 2 to equal 3x divided by 2. So we need to put something into x that when we multiply it by 3 and divide it by 2, the answer will be pi over 2, and then it will undefine the tangent function. The question I'm asking is, what do we put in for x such that when we times it by 3, we divide it by 2, it will result in pi over 2, thus causing the tangent line to have an asymptote. So that equation answers that. Cancel these two. Pi over 3 is equal to x. This is our first asymptote. So our first asymptote is going to be at pi over 3. So we've got, what have we got here? We've got 1, 2, 3, 4, 5, 6. My scale is 6, so these are pi over 6. So 2 of these is pi over 3. So there's my vertical line. What is the period? The period is going to be 2 pi over 3. So if this one is also symmetrical, there's no horizontal shift. So if this is at pi over 3, the other one's at minus pi over 3. And this is pi over 3, this is pi over 3, this is 2 pi over 3 between them. So the next one is going to be at 2 pi over 3. 1, 2, And then we're going to have 1, 2. I'd rather just count the dots. 4 squares apart. Once I figured that out, it was super easier. So next up, we need to draw our reference point. Our reference point is always, so there's no horizontal shift, so we're gonna go through here. The other point is halfway between these two always. I'm not even calculating. I could calculate it using the period, but I can figure out that it's gonna be a pi over 6. It's halfway between these two now. And the stretch is a half, so it's been moved down to there. So it's gonna go through these, and the curve looks like this. It's gonna go through here, it's gonna go through here, here. It's gonna look like this. And so on. You can't really see much of the. Sorry, can I just take this question? I got the question, how does the vertical shift work in a tan function? You don't really see much difference with vertical. Oh, sorry, vertical shift. Alright. You just move everything up. You move the 3 reference points up. So for instance, these 3 points here would go up, but your asymptote still looks the same. For a vertical stretch, you just multiply the reference points, which are at 1, by the vertical stretch. You can't show much more than these 3 points. The rest is just asymptotic behavior of its approaching the line. Should we sketch another one, or we've got time today, or should we move on? Because I've been given a scale that. Sorry, I've messed up. I've messed up a little bit. We're told in the question to sketch it in this interval. You would lose points for this. So I have to sketch it in the interval. So I'm going to have an end point there, and I have to have an end point of 2. Ooh, from 0 to 2. I think it should say 0 to 2 pi. I'll change that. 0 to 2 pi. So we do have to now show it going all the way up to this point here, which is an end point. It's going to go through there. It's going to go through here, here. This is the correct answer to the question. So the original reference points are 45 degrees and 1, or pi over 4. All right. Would you like to have a go at sketching another one, or would you like to? So let me just look at my lesson plan. I don't have too much to go through today. Let's move on. Let's move on. Have a go at writing a transformed function. Let's do it backwards. Gustav, stop. Stop. Okay, how do we do this? We're given this point here, which is sort of, we can tell that this is the characteristic point. The characteristic point normally lies at pi over 4. Oops. Pi over 4, comma 1. We've got 2 transformations. We've got A, which is vertical stretch. A will transform the 1 into a 2 when we multiply. So 1 times A is equal to 2. What does that mean A equals? So A is equal to 2. Next up is the other one. 1 over B times X has to equal pi over 4. Sorry.
Wouldn't it be pi over 4 times X?
Yeah. Sorry, I lost it here. What have I done? All right, yeah. So we want 1 over b times x to equal a half. So the x value. No, sorry. I'm getting all off. Why have I lost it? Our x value should be should be a half. This has to equal pi over 4. So 1 half, which is what goes in from this new function, would be multiplied by 1 over b, and that would result in x normally being fed into the tangent function. So we have to solve this equation. This gives us 1 over 2b is equal to pi over 4. That gives us 2b is equal to 4 over pi, which gives us b is equal to 2 over pi. It would be pi over 2 times x, yeah. So f of x is equal to 2 tan pi over 2x.
So why is it around?
Where?
Yeah.
Why is it easy to 2 over 5 but then 2? Yeah.
Because it's 1 over b in the model given by the question. You can see it's going to work. When I put a half in here, which is the x value here at this point, I'll get pi over 4. And pi over 4 will generate a 1. I'll times it by 2, which will make it a 2. So I can see that when I put a half into this function, I will get 2 out. Have I got this one?
So it's negative. What is negative? Is 2. Because the reflect. If you look at the characteristics of the y-axis, is it b going to be negative? Because when we're calculating a point, we have to use the negative 2.8. So it's a then b is 3.4 c times 4, right? So it's going to be 1 over b times 3 over 4 has to be equal to pi over 4. Yeah. That's going to be 3 pi over 4 pi over 3, yeah, it's 3. No. B is 1 over 3. Just if we divide by 3 by 4, both sides, we're going to have pi over 4 times 4 over 3 pi over 4. So the values cancel out. And it's just 3. Then we will update is 3x. Yeah.
I moved the view.
It's kind of like what we're listening.
Yeah.
Oh, no. Oh, yeah, negative. Yeah. Negative. Let me try this. Let's just try it. So it would be, yes. This is what we did last time, because we know that high before. Right, and then that's.
So, there's no difference if negative or I think there is.
Oh, yeah, there's waves, and it's still possible. Okay, so that's, waves going to, and then your first one. To get to here.
I mean, it doesn't matter, yeah.
Right, but then. Like, you're not saying, myself, I'm not saying my brain. So I just want to test out what it's like. With my brain. Negative 2.
So you see how this is it negative? Something has to be negative, right?
A is negative.
Okay, let's have a look at this. Let's have a look. So we need to times a by 1 to get minus 2. A is equal to minus 2. We need 1 over b multiplied by 3 pi over 4 should give us pi over 4. So cancelling, these two cancel, this cancels, that becomes a 1. So we've got 3 over b is equal to 1, b is equal to 3. Our function f of x is equal to minus 2 tan x over 3. This is the function.
That's close to one. Oh, wait, that's what I
Yeah. Now, sorry, Sid, can you not fall asleep in class? There is a lot of debate whether A or B should be negative on this one. There's a lot of debate whether A or B should be negative. Both will give the same. Both will be the same function. Why are these the same function? We have a couple of rules that we saw earlier in the course. And this is the sine of minus x is equal to minus sine x. We have the cosine of minus x is equal to the cosine of x. We have the tangent of minus x is equal to tan x. These are some of the trigonometric relationships we saw in the first unit. Let's have a look why. From a function perspective, we've seen it from the unit circle perspective. From a function perspective, it's saying that there's no point having a minus sign inside for the cosine function. What does the negative inside the bracket do? Reflection across the y-axis. The cosine function looks like this. So reflecting it here across the y-axis is going to make no difference. It's still the same. So from a function perspective, you can see this relationship, cos of minus x is equal to cos x, makes no difference. You can see this in the unit circle like this. So this is theta and this is minus theta here. And they have the same cosine value. They have the same cosine value. That's the same as this one. Whereas in the sine one, we have this around that point. We create a horizontal shift. There's a vertical shift here. It's the same with the tan function. From a functions perspective, this is the definition, negative tan x. From a function perspective, which one of these are odd functions? Sine and tangent. Because if you remember, the definition of an odd function, for an odd function, we say that f of minus x is equal to minus f of x. The sine function and the tan function, they're odd functions. You can just move the minus sign through. Whereas the cosine function, what type of function is this one? It's an even function. We can just throw the minus sign away from inside the bracket. We can just throw it away. Doesn't matter. This is an even function. This is where f of minus x is equal to f of x. This is odd. F of minus x is equal to minus f of x. And you can see the symmetry in these ones. All right. Last question. Modeling. I'm going to do this one for you. A climber is ascending the face of a 500 high vertical cliff at 5 feet per minute. Her climbing partner is observing her from 150 meters away. So let's have a little sketch there of what we've got so far. We're going up in that direction. Our partner's over here. A little bit more like that. So we're going to go up 500 feet up to here. Partner is at 150 meters away. She's observing him in that direction, assuming she's a midget of no significant height. Find a function that describes the amount of time climbing as a function of the angle of elevation. So the angle of elevation is this one. We know that the tangent of theta is equal to the opposite over the adjacent. So find a function that describes we also can describe the height in terms of t. He's climbing at 5 feet per minute. 5 feet per minute. So his height is 5t. His height is changing along this direction. So his height is the opposite, which is equal to the adjacent, which is 150, times the tangent of the angle. We need to find a function that describes the amount of time climbing as a function of the angle of elevation. So the amount of time climbing is 5t is equal to 150 times tan theta. So this is 30 tan theta is equal to t. There's the function. What is the domain of this function? What is the domain of this function? Can't quite work out the domain yet. The domain is going to be from 0 up to something. So the angle to begin with is going to be 0, but the domain will have a maximum. The domain will have a maximum. What will the maximum be? He's going to stop climbing when he gets to 500 feet. The range is going to be 0 is less than or equal to, so it's the height, isn't it? So this function here, h of t, is going to have a range of 0 to 500. That means we need to work out what the angle is when we reach 500 feet. So we can use this. We can say that tan of the maximum angle is the opposite, which is 500, divided by the adjacent, which is 150. So theta is equal to we need arctan of 500 over 150. It's 1.28 radians. Let's have it in degrees. 73.3 degrees. So the domain of this function goes from 0 up to 73.3 degrees.
Does the viewing angle ever reach 75 degrees?
No, that's outside of the domain. That would mean a height of more than 500 feet. So you can't reach that. That's me finished for today. I would just like you to work with the worksheet today. I don't have any IXLs for this one.